Okay, since I haven't gotten any questions on the quiz, we'll just move on to March 2nd. So starting from March 2nd, we have some retrosynthesis that we didn't go over. So last time we finished at this retrosynthesis question. So for now, we're going to be starting on the fourth question on March 2nd. So it's basically a cyclohexane that becomes this open chain with a few different two different carbonyls on it. So I'm going to give 2 minutes to figure out this question. Okay? Because this one is very easy. I do want you guys to send me your answers when you're done. All right, so usually you're going to start off by adding a functional group onto this. So the best way to do that would be Br2 or Cl2, but you have to do the free radical mechanism. So I'm going to do Cl2 over light, and what that does is it just adds one Cl to one of the carbons, because all the carbons are equally stable, so it could go anywhere. After that, we're going to use a base to eliminate it. And you shouldn't write the word base. You should actually write out your base, but just to save time. So then after that, we're just going to do 2 simple steps. So it's going to be, let's see, it is first, well, there's actually a few options, but the one that he's looking for here is basically to do OSO4 first, and then, so OSO4 to create the 2 OHs, and they're going to be cis to each other. And then after that, HIO4. So another option is from this section to just go, like, here, I'll draw this way. Another option in an alternate color, I'm going to do green, is to go from here to here with just O3. Now, or actually, I think you have to do like 1 O3 and 2 H2O or something, or H2O2. I can't remember exactly what ozonization is. Yeah. So anyways, those are your 2 options. Yeah. So this one wasn't too bad. Let's move on to the next one. So for the next one, we have cyclohexane with a methyl goes to cyclohexane, or really an aromatic ring, carbonyl, some more methyls. All right, and for this one, let's just do 2 minutes again. All right, so for this one, first, I would start off by doing a MBS. So with NBS, what we're going to do is we're going to be adding something to the benzylic position. So that would have a BR being right here. From here, what would make sense is to change this into an MG, so MgET2O, and what that gives us is something that's ready to be used in a Grignard. At this point, you can kind of use it actually in a Grignard. So the first step is going to be to, I mean, there is a possibility to do it in 1 step actually. So let me show it first in 2 steps and then 1 step. So in the 2-step portion, what we're going to do is we're going to react it with a carbonyl that has a hydrogen on one side and 2 carbons on the other. So then we get this. Yeah. And then after that, we can just go ahead and we can do PCC or something, and that will create a ketone. So another option, if we want to do it in 1 step, green. So from here to here, we can just do something that like kind of breaks off. So we could do like a something that looks like this and has like that on the other side. And yeah, I can't. What goes in the bottom of a Grignard, guys, is like H2O2 or H2O or something. H3O plus. I think it's H3O plus. Yeah. Yeah. Does that step work? This one in green? So, yeah. Okay. So, yeah. So if you want to do it in one step, you can do the green, or if you want to do it in two steps, you can do the black. Now I'm just going to look at your guys' answers and see if there's any differences here. Okay, seems like everyone pretty much came up with the exact same solution. But I do want you to know that there is that option to do in one step, because almost everyone did the two-step process. You don't have to do the two steps. You can easily do the one step on its own. Okay, all right, now let's go on to the next one. So for this next one, we have again 2 more minutes. Okay, so this one is also something I'd approach with Grignard. So first, I kind of want to add something to this side of it right here. So there's really like a few ways of doing this, but I'm gonna go ahead and I'm gonna add a BR, and then I'm gonna change that into our Grignard. So I'm going to do a anti-mark HBr. So that would be HBr on top and H2O2 in the bottom would do it. So that means that we're going to get a BR on this side. So then we do Mg Et2O, and that gives us this. Then from there, I'm just going to attach that. Let's just do the one-step process here. So I'm going to attach it to this. And I'm also going to have H3O plus. Okay. So then also another option. Actually, you know what? I don't really like one-step process as much because it's hard to get only 1 mole in there. So you might get multiple reactions. So I'm going to go back and I'm just going to do the 2 steps separately. So the first step will be this H3 plus, and then we get this. And then after that, I'm just going to do PCC. So another option would be to take it and do the opposite route. So a way of doing this would be taking this and changing it to an OH on the right. So a way of doing that is V2H6, V2H6, and H2O2. That gives us this. So then you can change that to a you can change that to a ketone. How can we change that to a ketone? There's 2 options. There's PCC or Jones. I believe PCC is the correct, right? I think it's PCC. I haven't looked at the notes though. Is it PCC?
Yes, it's PCC.
Okay. PCC, and then from there you can just attach that as the, or no, it's going to be 2 more steps. So you can attach your Grignard, which will be just this. So MGBR, H3O plus. So that gives us this, right? And then from there you can just, again, PCC. So there's really 2 different ways of taking it. You can either view that OH that you're adding as a ketone and add an OH, or you can view it as the MGBR portion. Let me just look through the answers that you guys sent. Everything looks good. A lot of you guys chose the second option, which is interesting because It's really something secondary that I thought about. The primary way that I thought about it was the other one. Okay. All right, not bad. Okay, so now next one. For the next question. Oh, we're done. Okay, we're done for the retrosynthesis. So let's move on now to just general reactions that he's going to go back and talk about epoxides. So epoxides are kind of like, they're basically a triangle with an O in between. And we also have ethers, which, as you guys already know, is basically this. Whoa, okay. Yeah, so an ether is like this. So the difference between an ether and an ester, the ester was the one that had a carbonyl and then the oxygen. So then he has a few different other definitions. He has THF, oxetane, and dioxane. But I don't think you really need to know those that much. THF comes up a lot though. Okay, so this is just like really a review. So remember, if you have two primary alcohols, what you can do is you can react them with H3O plus and some heat. And what you get is you get those two attached together, and it's like an etherification, basically. It's taking two alcohols and kind of putting them together. We already went over that mechanism, so I'm not going to talk about it again. Now here's something that's kind of new. So basically, this isn't the only way to do etherification or etherification. I don't know what the right word for that is. But the other way is if you have like a double bond like this, what you can do, it's actually really interesting, is you can almost look at it like a mark and anti-mark type thing. So what happens, and this is like something that's really new, if you have CH3OH and you have H3O plus, what happens is that the O from the CH3 portion is going to attack this side where there's possibly a positive charge, right? Right. So basically what's happening is that the oxygen attacks that side. And so what you get is you get the oxygen and that other carbon, and it looks like that. Okay. So this portion basically came and attacked the left side of the double bond, and a hydrogen came and attacked the right side of the double bond. So those were both added to a double bond. So that's really new, and watch out for that because it kind of takes a lot of people by surprise. And if you guys have any questions, let me know in the chat. Now, so we're gonna talk about Williamson. So in Williamson, this is actually a whole nother topic that we're gonna be starting. So in Williamson, I can't believe this is actually really late for like right before. I think it's because we were behind actually on the lectures. So if we need to, I might add something this week because we're a little behind. Let's see how much we can finish today. So for Williamson, what happens is that you take a primary alcohol, right? It looks like this. What you can do is if you react it with Na, that just becomes O minus with an Na plus hovering near it. Then if you add something with a good leaving group on it, so it could be an I, it could be a Br, whatever it is, basically this will protonate, and that gives us this. And then the negative charge from the oxygen comes and attacks it. Okay, so you can imagine that we get something that looks like this, basically. And similarly, you guys have seen this before. So if we're given this product, try to figure out what it came from. So again, remember that one of them has to have an O and an Na or a K plus, right? So the other option is an O and a K plus. And the other one has to have an I or possibly a Br or something like that. A good leaving group that is a halogen probably. So let's examine a question that asks it backwards. So first he'll give you this aromatic ring, and this is just an example. like that. So you have to figure out what are the two pathways and which one was most likely, right? Or actually, I don't think you need to say which one's most. Yeah, you do. So basically, let's break this up into pathways A and pathway B. So pathway A is assuming that the oxygen was part of the other side. So what that is assuming is that it looked like this aromatic ring, and then it had like a Br here. And that was reacting with O like that. Okay, so it's assuming that this was the reaction that was taking place. And if we look at this, this one basically, let's see. Yeah, so if these two reacted together, that would give us the appropriate answer, which is this. Okay. Similarly, let's go on to the green one. So in the green pathway, we're assuming that the oxygen was on this side. So it looked like this. And we're reacting that with maybe like a Br here. So in this case, you have to kind of think back onto your sheet a little bit, right? So according to your sheet, wait, let's see. I don't really see what he's trying to say is the answer here for this case.
I think root A is the answer because if it's a secondary halide, then there's a chance it will just be eliminated. Especially by a base that's as hindered as like,
yeah,
that thing.
Yeah, so what's going to happen is that this is going to lead to the, this portion eliminated that had the Br on it. And also there's going to be the other portion is left over. So the reason for this is because if you have a secondary halide, if you look back at your blue sheet, then a secondary halide can just be eliminated, whereas a primary halide is always SN2. So this one is the correct answer. So these kind of questions are definitely going to come up. So definitely practice them when they do come because they're take a little bit of getting used to. And also the blue sheet, like just remember the basics, a primary halide gets substituted, a secondary halide could get eliminated or substituted, but we're 100% getting substitution if it's a primary. So it's a much better reaction. Any questions? Okay. All right. So now we're moving on to 16.8. So here we have this, and it is reacting with HBr, and this is all new stuff. So this is just something you kind of have to know. Like, I mean, you can memorize the reaction, and I'll show you that in a second. Or sorry, the mechanism. Actually, you probably should know the mechanism because he hasn't shown that many mechanisms so far. So you should know. I think you should know the mechanism for for this one, which is two alcohols, two primary alcohols, and how they form an ether. I think that's a really good mechanism to know. And then also this mechanism is going to be really important. So this one, please just, keep this in mind. People get so confused about how this works. So basically, I'll walk you through the mechanism right now. So what happens is that we have this, and this actually has two lone pairs on it. So then we also have an HBr. Now what happens is that the lone pairs from here, they grab a hydrogen, and that gives us this with a hydrogen, and now it has a positive charge. So what happens is that this bond here goes back onto the oxygen, and the Br, which is now a Br minus, right? It became that. the Br minus grabs the CH3. So then this becomes what? It just becomes CH3 and Br, right? But this portion continues down here with, now that we've brought this bond back onto here, we have this. So this is an OH now, and it has, again, 2 lone pairs, no charge. So from here, another HBr, it's a pretty crazy mechanism, but I think you should know it. Another HBr comes along, this oxygen grabs the hydrogen, and the Br breaks off. And we have an H2O. And 1 lone pair and a positive charge. Then water is a good leaving group, so it'll break off at the same time as this Br. Oh god, my pencil died. You don't have to, by the way, you don't have to show the mechanisms for the BRs along the way. So I would just follow what he wrote in the notes. You don't have to follow like where the BR came from, because it's not necessarily the same BR. Like there's so many HBRs in the mechanism, so it doesn't really matter. But basically another BR minus is coming along and attacking that carbon. So this is the substitution. And then what we get is we get this with a BR in place of where the ether had been. Okay? Any questions about that? We're going to get a chance to practice this mechanism a few more times. All right. So second example of something like this. So this one, in this example, we're going to be dealing actually with a cyclized ether. So in this cyclized ether, we have HBr and heat again, just like the example above. And what that ends up doing is we have 1, 2, 3, 4. So 1, 2, 3, 4. 4 carbons and a Br on each side. Okay, so that's our answer. Now, how do we get here? So first, again, the whole thing we need to do is exactly the same. So starting with the mechanism, we have this right here. It has 2 lone pairs. So 1 lone pair is going to reach out, grab the H from the Br. Br is going to break off. That gives us 1 lone pair and an H on it. Now, what's going to happen is that the Br minus, is going to come and it's going to attack the carbon right before it. Either side, whichever one you do, it's fine. And this is going to go back onto the oxygen. That bond, the lone pairs are going to go back onto the oxygen. So now what we have is we've broken our cycle. I'm just going to keep the general shape so that you can see it. And in this case, now we have 2 lone pairs in the hydrogen. So from here, we're going to use another HBr to basically the lone pairs are going to reach out and grab the hydrogen. That was not very clear. Yes, they're going to reach out, grab the hydrogen. Bromine's going to break off. We get H2O and a positive charge. At this point, it's a good leaving group, so this is kind of the final step. The last Br attacks this side, and the water breaks off. And what we end up with is we end up with this. Then when you add it all together, so it's basically carbon 1, carbon 2, carbon 3, or sorry, 4 carbons together, and then 2 bromines on each side. So that's the same. Okay, questions? All right, no questions. So that's it for that. A good mechanism to know. There's a cyclic version and uncyclic version. It'll work the same regardless if there's other stuff on there. You just need to make sure that you don't change anything else and maintain the proper structure the whole way. So now we're moving on to some more like reactions. So I don't know if we did these reactions before or not, but anyways, it's good to review. So in this example, there's a double bond and we're reacting this with H2O and Br2. And again, like, you guys need to have lists going of all the reactions that he's taught so far so that you can kind of know them when they come up. So what this is going to form is it's going to form the cyclohexane. It's basically going to add on an OH and a Br. And it's going to add them on in anti-addition, right? So if it's anti-addition, we probably know that it's following Mark if that was relevant. It's not really relevant because there's equal amounts of hydrogens on both carbons. But the way that they're anti, we know that it's probably Mark, in case that was ever relevant. NaOH and H2O. So this is something that's new and really important. What this does is it takes an OH and a Br and turns them into an epoxy. Now, when you have an epoxy, they're both syn, and there's an oxygen there. So these two series of things can take a double bond into an epoxy. All right. So then let's practice that example one more time, a little bit. It's actually the same. So here we have this. Now it's reacting with Br2 and H2O. So this is basically like you can switch it, like it's either H2O on the top, Br2 on the top, it doesn't really matter. But basically what happens is, and we definitely, now I'm recalling this, you guys definitely know this from before. The difference was that if you have like a double bond and you react it with Br2 and like nothing in the bottom, then you're just adding two Brs, right? So that's kind of the thing. So anyways, if there's an H2O, then you add an OH and a Br. So after this, we just have to use the same thing, NaOH and H2O, and then that gives us the epoxidation. So that'll just look like this. Okay. All right, so, we're also going to speak in 10 minutes at 7 o'clock for 10 minutes. And then can you guys send your net IDs in the chat so that while you guys are on break, I can enter that. So here's another example. HCl. He says cold. Okay, interesting. Okay, so JD said she already entered them. Thanks. Yeah, no need to send your net IDs then. Okay, so HCl and it being cold. What that leads to is it leads to kind of a reversal of our esterification. So what happens is that it's the OH and that other thing break off from each other, right? So the OH is going to stay to the left, and our Cl is on the right. So how did we know that it wasn't a here to begin with? Because we don't want a secondary Cl. We want our Cl, our halogen, our leaving group to be primary so that it becomes substitution for sure. Now, if we do something one step farther, we do HCl and we do warm heat, then what that gives us is it changes this to a Cl as well. So that's possible. Okay. So wait, let me see, guys, just a second. So, here's another question right after that. So this is the same kind of principle. So we have this HBr and cold. So what this will do is it'll just, again, it'll take the H and it takes it to the H has to go, the OH has to go to the left side because we don't want a secondary halide right away. So this looks like this, OH here. And then the Cl's on that side. Or sorry, Br in this case. Okay. So from here, we can just go and use the HBr and hot, and then that changes to a Br as well. That's it. Okay. So then he shows the mechanism for that. You should look at that and see. But it's very, very similar to what we've just done with the oxygens, with the esterification. All right, so this is actually the most important part of what we're going to talk about today. So reactions with epoxides. This is going to be a huge topic on the exam. So epoxides, right? So epoxides aren't always what we've been drawing so far, which is like a very balanced triangle thing. Sometimes it can have some kind of group or mixture of groups on both of these carbons. So, and also sometimes it could be like a complete ring, right? So it's really not as simple as it's been looking so far. So in this case, so here's one thing that we can do. It depends whether it's going to attack this side or this side, depends on what is reacting with it. So if we're reacting it with NH3 and H2O, what that's going to do is it's going to add an NH2 group to the right side, or to the side that has the least carbons off of it, or the most hydrogens you can think of, right? So this side has more hydrogens, this side has less hydrogens, right? So you can think of it like the NH3 adds to the side with the more hydrogens. And because it attacks, so like imagine this, imagine the NH3, or sorry, NH2 minus, imagine attacking this carbon. That would break this off, and so now our oxygen is on the other carbon, okay? So that's kind of the reason why we know where our OH is. You can't draw it like this with your NH2 here and your OH on the same carbon, right? The OH, the O breaks off here so that it ends up being on this carbon. All right, so that's the first reaction. Secondly, we can also do Grignard type reactions with this. So if we have here the example of a cyclohexane that is an MgBr. So an MgBr reacting with this same molecule, right? And then also T2O and H3O plus. Okay. So with those reacting together, the Grignard is basically, it's a negative charge, right? Let me just equate this. So this is basically a cyclohexane with a negative charge. The negative charge is going to attack again the right side, the side with the most hydrogens. So what we get is we get this. And on the other side, we get OH. Okay, next. So in this case, we are going to be adding a simple hydrogen. So how does a simple hydrogen work? So we can use LAH, for example. As we know, LAH is basically the addition of a hydrogen. So in this situation, and we have LAH, what happens is that the H minus, or sorry, the H plus attacks, no, an H minus, sorry. The H minus attacks the side with the most hydrogens. So think of it like a mark type thing. So it goes to the side with the most hydrogens. And that means that this is going to break off and the OH is going to be left there. So we get this as our answer. So these were all basic. How do we know that they were basic? So the way that we know that they're basic is because, for example, right here, this was an NH2 that reacts. And NH2 is negative charge, right? You guys get that? So these are basic reactions. Basic reactions with epoxy. So in this situation, it was H2 minus. In this situation, it was an aromatic ring minus. So again, a base, right? And in this situation, it was an H minus, so a base. So every time a base is reacting with an epoxy, it goes to the side with the most hydrogens, okay? So base goes to side with more hydrogens. Now let's look at acids. So in acidic reactions, wait, let me see. I don't know if that was the best way of putting it. Okay. I'm not sure whether it's about the solvent or if it's about the actual nucleophile. I'm not totally sure. But anyways, because like the reason I don't think it's about the solvent is because the solvent here is an H3O plus. What do you guys think? Is it about the solvent or about the actual nucleophile? The only thing I noticed is that for these questions, all the nucleophiles were basically bases.
I think in order to get like the OH, the solvent has to be protic, but that's about it.
Okay. Yeah, but I'm looking at the acidic ones, and they're also kind of like O's, like they're negative charges attacking. Let's take a look at this. So there's the acidic ones. So acidic epoxy equations, or sorry, reactions. So in this case, he has two methyls on one side, one methyl on the other side. Reacting this with a primary alcohol and H3O plus gives us the OH. So it basically attacks the side with the least hydrogens. So the side with the most hydrogens gets the OH, and the side with the least hydrogens gets the attack of this. Maybe it depends on the mechanism. Let's look at that in a second. Okay. So then this next one has the cyclohexane epoxies right here. So clearly there's a difference between which ones has the most and which one has the least hydrogens. So HBr. So in this case, the Br is going to go to the place with the most hydrogens. So you notice that acidic equations, the nucleophile goes to the least hydrogens, and in basic ones, it goes to the side with the most hydrogens. And I think that makes sense because if you want a hydrogen, then you're going to have to go to the side that has the most hydrogens. But I'm still trying to figure out how we know the difference between whether it's basic or acidic. You guys have any ideas? Like, what makes these acidic problems as opposed to the previous three problems? I
mean, it's because they're protic, I think. Like, they're very, very obviously protic. Like, when you think of something that's protic, you think of like HBr, you think of like an alcohol. Whereas you kind of have to just memorize NH3, but everything that comes before it is like pretty clearly not what you think of when it's protic. I don't know if that makes sense or not.
I don't really think of HBr as protic. I mean, protic has to do with the solvent.
Right, but it has a proton. It will give off a proton. It is a losable proton. It's, you know, protic looking, sounding.
Yeah, I mean, I'll be honest with you guys. I just memorized these. Like, there's only 5 of them. So I kind of memorized them. Based on, so if you go to the page below that, he has like every single question he could give you with an epoxy. And I just memorized all them. But I think I'm gonna probably meet with him and ask him real quick how we know. I feel like there should be an easier way of knowing it though. But I mean, I see what you're saying. Yeah, that like some of them are protic, some of them are aprotic. But I think that negative charge is something that's really important because like he did highlight them multiple times. I think it's because I'm not quite sure of the mechanism for both of these. I have a feeling that what happens is that this takes one of its O's and grabs the hydrogen first, and then a Br minus will come along and attack here. That's my feeling on the mechanism, but again, like I have no way of knowing.
Yeah, that
Well,
feels about right for me too, because it feels like the O grabs onto the positively charged H,
yeah,
and
it
then
always,
everything else happens. We saw this previously when we were doing cyclized ethers, I think, like
yeah,
with the
that's always
HBr.
like always what happens. And it's probably the same for this top one, honestly. This would grab the hydrogen first. Um, but then again, I'm not sure because I think it might have something to do with it. Like it could be getting hydrogen from here first, so then maybe this really isn't a base attacking. Maybe it's attacking and then the hydrogen protonates. I'm not sure. But yeah. So I'm gonna talk to Dr. Sutton about the difference between acid and base epoxides. But in the meantime, I honestly like if it makes sense to you, then good. If it doesn't, if what JD said makes sense to you, then good. But if not, just memorize them. There's only 1, 2, 3, 4, 5, 6, 7, 8. There's only 8 possible reactions with an epoxy, so it's not bad at all. And let's go through those reactions. So in this example, we're going to be using this over and over again for all of our reactions. So there's going to be 8 of them. So that's 1, 2, 3, 4, 5, 6, 7, and 8. Okay. And as soon as we're done with this, actually, let's take our break now, and then when we come back, we'll work on these 8 reactions, okay? So you have till 7:15. Okay, so we left off talking about the 8 different reactants that happen with an epoxy. So let's get started on those. So the first one is going to be, let's start with the bases. Okay, so we'll start with NH3. So NH3, as we discussed, is a base. So it's going to go to the side with the most hydrogens, and we're going to be left with an OH on the other side. Second base example is LAH, and LAH is going to leave a hydrogen to the right, which means that the OH is left on the left. Okay. The third example of the base is something like this with MgBr, for example, and H3O plus. And in this case, what it's going to do is it's going to go exactly like what we've been doing the whole time. The bases love to go to the side with the most hydrogens, so the OH is going to stay on the side with the least hydrogens. Then we have NaOCH3 and CH3OH. So this is just a strong base, right? And this strong base is going to go and it's going to attack the side with the most hydrogens. So I'm actually starting to suspect that he may have made a mistake, guys. First of all, what's going on here? Why does the answer have... Yeah. You guys see how there's an extra methyl right there? I think that's a mistake, I believe. I just don't see how it got there. Yeah. So ignore, when you're doing this one, in the March 4th lecture, extra methyl right there. I don't think that should be there. Okay. So those are all the basic examples, right? Base. 2 more hydrogens. Then let's start talking about the acids. So the first example of an acid is your basic HBr. HBr is like, oh, what was I talking? Oh my god, of course this makes sense. Yeah, HBr is a bit acid. Okay, so what happens is that this is going to promote CBr going to the side with the least hydrogens. So the OH is going to go to the side with the most hydrogens. The next example of an acid is H3O plus, which basically is going to add an OH. So it's going to add an OH to the side with the least amount of hydrogens, and then that leaves the other O to become an OH on the side with the most hydrogens. Then another acid example is basically going to look like this. So this is a phenol with H3O plus. So a phenol with H3O plus, like just because it's acidic, we know that the phenol is going to be added to, oh, sorry. The phenol is going to be added to the side with the least amount of hydrogens because it's acidic. I mean, yes. Then the last acidic example is CH3OH over H3O plus. So this is an acidic one because in the example where we had CH3ONA, that is a strong base. So this is the more acidic version of that. Okay. So because acidic version, it's going to add itself to the side of the least hydrogens. So just to review, this actually makes a lot more sense than the previous examples we did. So these are acids, and they go to the place with the least hydrogens. So looking back at these examples, yes, this is a more acidic version because it has CH3OH. So I don't think I really need to ask Dr. Son about this because this makes a lot of sense now. So this is basically the acid version, and CH3O minus is the base version. Or if you see CH3ONA, that's also the base version. Also HBRs, HBr, HI, HF, all those, whatever, they're all acids. This is definitely a base because it's just an H minus. This is a base because it's a phenol that has, a benzene ring that has a negative charge. That's a base. NH2, that's a base. Okay, so this makes a lot of sense now, and it allow in terms of acids and bases, and that kind of works out. So I really like that chart, and you should definitely take a look at it and like study it closely. Let's get started on our retrosynthesis because we have like another half an hour left. So actually there's one retrosynthesis question, and then he goes on to some other stuff before we continue with the retrosynthesis. So let's do this one retrosynthesis problem. So this is a cyclopentane, and we see that our answer is also cyclopentane. It actually has the same number of carbons overall, but we notice that we somehow added an NH2 to one side and an OH to another side. So you have to think very carefully about how can you do this. There's like hints. It's going to involve the stuff that we just talked about. So I'm going to give you guys 3 minutes to write a retrosynthesis and send a picture to me, okay? Okay. So for this one, if you kind of remember what we just talked about, it makes a little bit of sense. So one of the ways that this is going to work out best is if we change this into an epoxy and then attack it with the NH3. So the first way to turn it into an epoxy, the first thing we have to do is kind of add an Br and an OH, because that's the only way we know of changing something into an epoxy. So we can do Br2 and H2O. So that's going to add a Br to the side that has the most hydrogens and an OH to the side with the least. Then we do a OH and H2O to turn that into an epoxy. Then we're going to attack it with an NH3 and H2O, and that basically adds an NH2 to the position that has the most hydrogens. Now let me just look at your guys' answers real quick to check if everything works. Yeah, this one was fairly easy. You guys all got it right, it looks like. Okay, good job. So someone else also showed the other way of doing an epoxy, which is something that we knew from Orgo 1. So another way to make epoxy, and this is totally acceptable if you want to on the exam, but the reason you have to know this step-by-step process is because that could be in the other portion. But yeah, you can totally add, you could just go like this, and you can add like CH3C, or sorry, CH3CO3, and then I believe that's an H at the end. Yeah. So it can be any number of carbons beforehand, but the important 3H. So the reason I'd like you guys to watch out for this is it could literally be anything beforehand. It could be like this, and then CO. Oh my god, my pen just died again. This is so annoying. But it could be any shape or anything. As long as you see a CO3H at the end, that is going to cause oxidation. So any one of these, anything, as long as it's CO3H at the end, what it will do is it will cause epoxidation immediately. So that's another way of doing it. All right, let us move on back to the reactions. Okay, so back to the reactions. So he shows the other way of doing it. So the other way of doing it, which I just showed you guys, is CH3CO3H, and then go like this. That creates an epoxy. Then if you do HClO4, that is going to basically add an OH to there. Oops. So it'll basically look like one OH going, like the two OHs are going in opposite directions because they're anti-addition, and methyl stays there. So that's the way of making them anti. If you want to make them syn, then same situation, or let's just, yeah, so if you want to make two oxygens that are syn to each other, you just do OSO4, which we've already done before. So OSO4 turns them into syn. So both oxygen OHs are in the same direction. So just to review, for if you want to make them anti to each other, you have to do the intermediate step of epoxidation. So you have to do epoxidation and then HClO4. If you want them syn, there's no need to do epoxidation. Just go from a double bond to syn, okay? So double bond to syn. This one is double bond to epoxy to anti. So this is something to keep in mind whenever you're doing your retrosynthesis. Please pay attention to whether it's anti or syn, because that's going to inform whether you have to do epoxidation or not. Okay. And just to remind you guys, once you're here after the OSO4, or once you have your two OHs, what is the reagent that changes it from being two OHs to this? What is the reagent that does this? HIO4. So why did I bring that up? Because I don't want you guys to get confused between HIO4 and HClO4. So HClO4 is being used in this situation, in the top situation, to, let me highlight them in red, because it's just occurring to me how odd they are similar. Because, I mean, what's the difference between I and Cl? It's just, they're both halogens. I mean, I is definitely much stronger of a base or acid, or I mean, an acid, much weaker of a base. I don't know if that's what makes the difference. But yeah, so there's HiO4, which we use in this case where we have a diol, and we're changing it into a dicarbonyl, basically. Or HClO4, which is an epoxy, and we're changing it to an anti-diol. So pay attention to those. Okay, moving on. So here we have this, and it's going to do a few different reactions. So this, I believe, is a review of exam 1, where we're learning about, you know, differences between meta, para, and ortho positions, and we're learning about activation and deactivation levels. So for the first one, if we remember based on our chart, this is going to be a very deactivating, or sorry, a very deactivating, but wait a second. I just need to think through this for a minute. Because I can't really remember. I haven't reviewed this in a long time. I feel like it was deactivating and meta directing. Oh, it's activating. Yeah, no, this is the activating one. Activating and meta or ortho directing. So it's going to go to the para. Sorry, not meta or ortho or para directing. So the first part is that it's going to be activating and para directing. So it attaches that to the para position. Then we're going to have a chlorination. So for chlorination, we're going to have to consider like where everything is directing to. And so basically this is actually more activating. So it's going to go to the ortho position for this one, right? And this is just based on your chart, which I like kind of remember, but not completely. But I'm pretty sure that this is more activating than just an alkyl group. So it's going to go to the ortho position for that one. Oh, and on top of that, JD just sent in the chat, another reason it's more likely to go to this position than this position is that the bottom position is more hindered. But yes, also you have to look at which one's more activating, and it will more likely follow the more highly activating one. After that, HBr, so this is a reaction we just learned. It actually has nothing to do with all the rest of this stuff. What it will do is it'll basically keep everything the same. The only thing is that it will take that whole entire OCH3 off and replace it with an OH. That's one of the things we just learned. So go back up through the mechanisms if you forgot that.
In the mechanisms we discussed, that was BR at the top. I don't know why it says OH on the exam.
Yeah, I was actually thinking the same thing. It didn't make any sense. I think this is a BR. I think that is probably a mistake. Did you guys watch the videos? Well, I wonder if in the video he said maybe like, oops, that's a mistake. I don't know. But anyways, yeah, I think that should be a BR because based on the mechanisms we learned, it's a BR. So that could be just a little mistake. All right, next. So this is some other mechanism that we did, right? So in this situation, we kind of have to figure out, we're going to basically break the O and the BR from each other. So the O is going to go to this portion because we don't want the O as part of the other portion because we want the BR to be primary. So what's going to happen is that this is going to lead to this and this. So we basically broke it off. And there's a mechanism for that, but we kind of already did this mechanism. It's basically where this oxygen grabs a hydrogen and then the Br will come and it will tag this carbon right here. Okay, so this is another epoxy question. So this one should be really simple. But I'll ask you guys the questions. So here we have, all right, so we're reacting this with HCl. HCl is an acid, right? So it's going to go to the place with the least hydrogens. Interesting. But in this case, I'm not sure. I think I would need to watch the video to understand what he's saying here, because usually you can just tell. Does anyone remember what he said in the video for this question? I part of me thinks that there's just an equal portion, like it could go equally either side. You could end up with the Cl on one side or the Cl on the other side. That's what part of me thinks, but that's not what he's showing on the paper. He's showing that this is the answer. That the Cl went to the left. But I think it could equally go to the right or to the left, unless there's something different or defining between one of the carbons, but I don't think so, because he wrote that both of them are S+. So that means they're both pretty much the same. So it doesn't really matter which one goes which side. Oh, yeah, sorry, yes, this is a benzylic position of the Cl. Okay, I'll put a note of that. Yes, benzylic. So if it's benzylic, then it's going to be more stable. Good job. Okay, next. So this is going to have two different reactions. Okay, so for the first portion of this, just epoxidation, right? We're going to get this. And then for the second portion, we have to consider, is this acidic or basic? It is what? Is it acidic or a basic reaction? Just type it in the chat. Is this acidic or basic? Okay, I only have one response, but it's basic. How do we know it's basic? Because it says NaOCH3. Na is a spectator ion, which means that O is left with a negative charge. Oh, that's very basic. So this base is going to come, and bases tend to attack the side with the most hydrogen, so they're going to attack this side. So what we get as our answer is going to be this, with the OH on the top and an OCH3 on the bottom. Okay. By the way, I'm under the impression that almost every time you pop an epoxy, they're going to be anti to each other. Because JD, you asked about the stereohindrance of all of the 8 reactions we did before. And it's just my understanding that anytime an epoxy pops open, it's going to be anti. Like, I've never seen it syn after a epoxy pops open. Do you agree with me on that?
I've also never seen it be syn after an epoxy pops open, but I just wanted to clarify that that's like a
Yes.
rule.
It is, because it's kind of the way that epoxy works. So in epoxies, both of these are going to be syn, right? So we can't have something attack here as forward facing. It has to attack as backward facing, and then that breaks this. Forces it to always be syn.
Oh, okay, so that's why.
Mm-hmm.
Okay, that makes sense. Thank you, Fatima.
No problem. All right. So So this one involves a triple bond, so this is really good because this is end of last semester. I know you guys probably don't remember it because a lot of people just learn this real quick, take the exam, and forget it. But triple bonds. So when we react this with Lindler basically makes a triple bond into a cis double bond, okay? So that our double bond becomes cis, carbon, 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 OH. I'm just like following. Oh, no. Carbon, 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 OH. Never mind. That's too many. OH. And then on the other side, we have carbon, OH. Okay. So that's the products from Lindler. Then after that, it's doing H2SO4. H2SO4 is basically H3O plus, and as you remember, diols and H3O plus are basically going to form an ether. Since we have one molecule with two alcohols, it's going to be an like an intermolecular or cyclicization ether. So I'm just going to put my double bond at the top. I'm going to go down, so 1, 2, 3, 4, 5. So 5 of these plus 1 oxygen means that it's going to be a hexagon shape. And my oxygen is going to be closer to one side than the other. Actually, no, yeah, it's closer to one side than the other. One side of the double bond. Because this double bond has the one carbon on the double bond and then one more carbon than oxygen. So that's right there. The carbon on the double bond, one carbon to the left of it, and then the oxygen. So it's closer to one side of the double bond than the other. Okay, next one. So for the next one, we have, oops. Okay, there. So we have this. Okay. So the first thing that's going to happen is that, so this is a retrosynthesis. Do you guys want to try this one, or should we do it together? Let's give it a try because we only have, yeah, this is the last question we'll do today. So I'll give you guys 4 minutes because I think this one's going to be a little bit harder to figure out. So please take your time. We have four minutes for you to try this, and then send me your answer. So for this one, the best way to do it would be to somehow we need to get the double bond to occur between these two and then break that off. So actually, never mind. Yeah. So okay. So what I'm going to do is first I'm going to try to eliminate that. So a good way to eliminate this is just do H3 plus. So what that does, if you don't remember, is it basically makes this eliminated. And we're going to ensure that it goes to this elimination spot instead of here or here, because that's actually the most stable according to Zaitsev's rule. So after that, once we're here, we can kind of add an OH to, what we're going to do is we're going to do like an etherification. So to add an OH to that position, which is actually the position with the most hydrogens, I have to do an antimark addition of H and OH. So I'm going to do B2H6 and H2O2. And so what that does is it's going to take that double bond away, add an OH here. Then from here, all I have to do is react a second OH with only one carbon on it. And maybe like, I think it's H3O plus, I believe. And that'll basically cause the etherification of the two. So now I'm going to look at some of your guys' answers and see what you guys did. Okay, so someone did, instead of just doing the one step with H3O plus, there's another option. You can kind of go like this. You can take this OH, change it into a BR. This isn't the most efficient, but it's there in case you forget the other one. Then we can eliminate, right? And then from here we can just continue for the rest of the way. And I think that's all I got in terms of answers. Oh, I got one more. Let me see. Okay, yeah. No, that's it. All right, so I guess that's enough for today. So I'll see you guys on Wednesday. And on Wednesday, what we're going to do is we're going to finish up so we'll go back to NMR a little bit on Wednesday. You need to be practicing NMR in between. So we're going to finish up the NMR from March 4th. And then we are also going to work on, let's see. Well, first I'll start by taking all your guys' questions. Then we'll do NMR from March 4th. And then also I'll take practice exam questions. And we'll do March 9th. And the review for exam 2. All right, so what I might do is I might change the Wednesday review to 3 hours. Don't worry, there'll be lots of breaks and you don't need to stay the whole time, but I think if I really want to go through everything, I need to change the Wednesday to 3 hours or add another hour somehow, maybe on Tuesday. So I'll keep you guys updated. Either it'll be 3 hours on Wednesday or 1 hour on Tuesday, 2 hours on Wednesday. Either way, I'll let you guys know in the announcements. But you guys have a good end of your weekend, and I hope you guys all, keep up to date and like don't fall behind and do well on the exam, but also don't get stressed and all that kind of stuff.